Okay, we'll get started. Let me take a minute to. So I'm doing this from my office. I don't have, my desktop computer is not working. And on top of that, I'm using my laptop, so I just have one screen. So I feel a little handicapped today. Can you guys hear me okay?
Yes, sir.
Okie doke. All right, so let me bring up some slides. And let's see. And well, okay, maybe this is it. What? There we go. Okay, cool. And so, okay, so so the quizzes should be all okay for 1, 2, and 3, and everybody should have a a retake provided to them for all 3 of those. So if you can go ahead and do 1, 2, and 3, if you can do those, and today would be great. That'd be good to get kind of all caught up. And then I forget, I think 4s do. I don't know. See, let's look at the syllabus real quick. So,
4 is due on the 3rd.
yeah, let's see what it says. I forget.
No, it's due on the 11th. Sorry.
Yeah, I wondered because all of them I think are due on class days. So, yeah, end of chapter 3 is due on the 4th. So actually, so, and the quiz for chapter 4 is due on the 11th. Yeah, so you got some time on that one. I guess till next, is that Friday next week? Oh, it's Saturday. It's Saturday the 11th. Yeah. Okay. So yeah. Now where the reference to the homework here is. So I haven't created homework. So there are no homework you have to do. So remember, even though it says that, I didn't take those out because at some point I may give you some homework. But right as of now, there's no homework assigned except the end of chapter quizzes. Okay. So, all right, and so we should be working on 4 today, and we'll work on 4 again, not on Monday because that's Labor Day, but on Wednesday, and then on Friday we'll be on 5. Okay, so let's turn to chapter 4, and let's see.
Is the notes on Blackboard for today?
They're not on Blackboard, but I'll go ahead and put them on right now. I just didn't get them on yet, but I'll do that. So let's see if I can get on Blackboard.
Hey, Professor, I had a question.
Sure, go ahead.
So are the quizzes still kind of have to be like a essay type questions, or did you rewrite them so they're like?
I rewrote them. They're
okay.
all machine creatable. So they're either multiple choice. In some of them, where you have to draw a circuit, I gave you 4 example circuits. You have to pick the right one. Things like that. So they're all either multiple choice or they're true false. Are their numbers. They're all machine creatable.
Okay, because that was confusing when I took the chapter 3 quiz.
Well, it's because they had, even though I had done that quiz in June, they had not updated it in the book. So some things that just didn't get done, and because they were working on other stuff, I guess. I don't know. But in any event, I think they've been working hard this week to get that all caught up. And in later chapters, I think things are more were better because those quizzes. So as I went along, well, I didn't really, there were a lot of things I didn't know and they didn't explain. So if you ever decide to write a textbook, talk to me. I'm still around, but there were some good questions they asked at the beginning that I didn't know to ask. But anyway, so I was kind of, so I sort of made the end of chapter quizzes. They weren't like a big thing initially. And I made the questions so they were, so you just had to type in stuff, but they weren't really gradable. I didn't really understand, what their process was, whether they could even do anything gradable. And it turned out their online process very similar to the Blackboard stuff. But in any event, so I had to go back and redo all the quizzes and make them machine gradable. And that's what I did. And the last few chapters I had already, I hadn't done them yet. So I ran ahead and did the quizzes so that they were machine gradable and that they were, and I tried to make them all. Most of the quizzes will be 10 questions from here on out. They're not all that way, I guess, but most of them are. Anyway, it was just an exercise, a little bit of, it was a little bit difficult to have to redo everything, but I think it's all done now. And I think they've gotten it mostly all updated, but I will now be working ahead and hopefully I'll make sure the quiz for 5 and 6 and 7 are working correctly. I found one mistake in grade in one for 4, and hopefully they fixed that. So I'll double check that early next week, but it should be good. I think we're back on track. Okay, let me put these slides on Blackboard.
I had issues with quiz 1. I couldn't do it. It said it was expired.
Yeah, you right. They timed out. You had two chances to take them, but there was a date they were due, and after the due date, you couldn't take it. But I think I gave you a retake, and I believe the dates were moved. I moved the dates, so you should be able to do it now.
Yeah, it still says it's due on the 28th, and it's already passed. It didn't open up for me. I don't know why.
Did you try it? When did you last try it?
Yesterday.
Okay, well, yeah, I reset those. I think I reset those on Wednesday. All right, that was for 1? Maybe I thought everybody had gotten 1 done. I'll look at that. I'll look at that tonight and try and get that fixed so you can work on it this weekend.
All right, thank you.
But go ahead.
Can you send us a confirmation email when you reset it so that way we can go in there?
Okay, I'll send an email to the whole class when I reset quiz 1. Was anybody able to do quiz 1 yesterday?
I wasn't able to do it.
Okay, all right. So it sounds like it's a problem. All right. Okay, so let me go back to content. And then what I will do is, man, this is so slow. Okay. I wish Norton would stop.
I just went there. I think the date's still the same, but I think you're able to take it because I did it and suspended it. Just the date's still the same though.
Yeah, that sounds reasonable. I think maybe when I authorize the retake, it's different. I think it's a different format, so it's not the original. Yeah, so it should be, you should be able to take it. But yeah, so it sounds like you could. Okay, so go ahead and do it. I think it's okay, but I'll go. And I have no way to check it because when I do it, it doesn't treat me like a student. So I'm not always sure if it's going to work correctly for you. All right, but anyway. Yeah, okay. All right, let me log into Blackboard and I'll post the video. I mean, post the file. Okay, and then I want to go down here to PowerPoints, and I think slides from Morton Book. Click on here, and then add file. And this will be chapter 3. The 1 for 1 is really chapter 1 and 2. And then we want to go to should do it. Let's see. Well, yeah, except I should label them 4. So let me fix that. Okay. All right. So those are the slides I'm going to use today. And I guess I can, well, I've got my already set up. Okay. Then let me do that. And then let me do this. And then let me do this. Let's see, I do want to put the, see if I can put this there. Oh, I want to share the screen. Okay, share screen and share. Perfect. Okay, looks like it's going to be fine. Okay, and then we'll do this. Great. Okay. All right. So here's what we're going to try and get out of it. We've already covered a little bit of this. I want you to be able to. What we're going to cover today are the theorems of switching algebra, and these are everything you can do with switching algebra. So the theorems are pretty important, and what you have to do is you have to you don't have to. I don't want you to necessarily sit down and try and memorize them. I just want you to use them to become familiar enough with them. And then you'll realize that most of them you can just figure out in your head. And there's maybe 3 or 4 that you actually have to memorize. They're very straightforward. But hopefully if you use them a few times, you'll almost have them memorized. You'll just have to just make sure you kind of, pay attention. But you can, when you do the test, I'm pretty sure I'd give you the someplace to reference well, you can look at the theorems because you can do it open book. All right, so you don't actually have to have them memorized, but if you haven't used them enough to pretty much know the ones you need to use and pretty much know what they look like, you're probably not going to be able to use them effectively. All right, so you should be able to write out the 3 theorems, the theorems for conversion, the key theorems for simplification. You need to be able to simplify a logic expression within reason. I mean, there are some that are really complicated, but the fairly straightforward ones you should be able to do. And you should be able to convert from SOP to POS to POS to SOP, which is and/or a 2-layer and/or network to a 2-layer or and network, and vice versa. And you should be able to invert a logic expression using De Morgan's law. So this is what I want you to get out of chapter 4. All right. How to approach switching algebra. So you need to really think about this differently. This is not regular algebra at all. It is completely different. Looks the same, it's not the same. And so for that reason, you really need to try and put out of your mind regular algebra and just start with a blank script. Because if you think a lot about regular algebra, you will it will be a problem. See what happens with that. Okay. So for instance, in switching algebra, our variables don't really mean numbers. They mean true or false. And we usually assign 1s and 0s to them, but that's just a notational convenience. They don't mean the value of 1 or the value of 0. They mean true and false. So A plus A isn't, if A is 1, isn't 2, it's true. So you just have to think entirely differently. So the symbols, the variables are symbols that are not numbers, even though we use 1 and 0, where 1 means true and 0 means false. So we're really talking true, false, okay? So just think, my variable is a symbol, it's not a number. The fact that variables can only have 1 of 2 possible values has a huge impact on the practice of switching algebra. It changes everything. When you write the value x in regular algebra, how many possible values are there for x?
an infinite amount depending on the
It's
function that you're
infinite.
using.
That's
Yeah.
right, unless there's certain bounds put on X. But even if you restrict X to the interval from 0 to 1, it's still infinite. Now, if you force X to be an integer, if you don't put bounds on it, it's still infinite. But if you do put bounds on it, okay, then it may be countably finite, or it may be a fairly small number even. But generally speaking, just the variable X has an infinite number of possible values. But that's not true in switching algebra. There's no variable that has an infinite number of values. There may be very big multi-bit vectors, but they still have a finite number of values. Okay, so the fact that the variable can only take on one of two possible values has a huge impact. It means that most expressions with a reasonable number of variables in it only have a few possible. You can quickly explore all possible values of the expression, and that's huge. That allows you to do proofs. So there's no such there's also no such thing as addition, subtraction, multiplication, or division in switching algebra. None of those things exist. We have borrowed, or perhaps better, stolen the notation of addition and multiplication to represent anding or oring and anding. But we're not actually adding, we're not actually multiplying, we're actually oring and we're anding. So there is no such thing as addition, subtraction, and there's definitely subtraction, and there's no such thing as multiplication or division. All right, everything in switching algebra can be proved or disproved. If you write a relationship, you can prove or disprove whether it's true or not. There's nothing that's so complicated you can't prove it. There are many things like that in the real world of algebra. People get PhDs and Nobel Prizes for solving some of those conundrums. It's not true in switching algebra. Switching algebra, nothing is left unresolved. You can prove or disprove everything. Almost in many cases, not every case, but almost all cases, but many cases, we have multiple equivalent solutions when, say, we implement a truth table. So that gives us a lot of different ways of representing the same hardware, or maybe a better way, same logic expression to be implemented with a number of different equivalent sets of hardware. All right, when you do switching algebra, avoid going in circles. It's really easy to go in circles. I remember when I first started doing it, I would have a whole page of lines, and then I'd switch to another page, and then son of a gun, I realized that I was back to where I started, and I had never gotten to where I wanted to go because I started applying the same formulas in reverse. So what you should do, you should write down the formulas you're using. Again, there's only a handful, they're very simple, and put an arrow on top of the formula to show which way you're using it, because you can use them either way. And then make sure that those arrows are pointing in the direction you want to go, and then check it, and don't ever apply the formula in the wrong direction. Now, you might have to start over because you might go down you might take a path that doesn't work and you might have to start again. That's fine. But when you're working, don't start suddenly applying your formulas backwards and get back to where you started and be very frustrated. So put an arrow, write the formulas down and put an arrow over the top of them each time you use one. And that'll really, especially in the early going. Now, once you get maybe a little experience, you can skip that, I guess, but I still do it. Well, I don't actually, but I do it in class. Before you start trying to convert from, say, the AND/OR form to the OR/AND form, which is the SOP to POS conversion, or going the other way, POS to SOP. Before you start, look at your expression and make sure you see what form it's actually in. And then if you can simplify it with one of the simplification laws we're going to cover in just a minute, do that first, because that'll make your life so much easier. Remember, the theorems we're going to cover here, the 16 or 15 theorems, that's all you can do. You can't do anything else. There's no other things you can do. Try some different approaches. and keep where you're, keep the form you're going for as your target. Keep that in mind. Make sure you don't lose sight of that, because that's when you start going in circles. Okay, and can't see this. Oh, there, I have some hints listed at the end. So make sure you take a look at the hints at the end. We'll cover those in just a second. All right. So next we're going to cover the theorems, but we're going to take them one group at a time. And there are 4 groups. There's the trivial theorems, which are pretty obvious. Simple things like X or X and X and X, X ANDed with 1, X ANDed with 0, X ORed with 1, X ORed with 0, that kind of stuff. X, Y, Z plus ZY, does that same as ZYX plus Y, X, Z or what? And yeah, it is. So the trivial theorems. Then we're going to cover the simplification theorems. There are 4 of those. And then we're going to cover the 3 conversion theorems, just 3. And then we'll talk about De Morgan's laws, which basically is your inversion theorem. And then we'll also talk about what a dual is and how you take the dual. So it turns out that all of these other theorems more or less have dual forms. And so they'll be listed in the chart. Okay. You only have to memorize a few critical ones. That's it, maybe 2 or 3 at the most. All right. So here are the So here are the trivial laws. I'll put this down. Oh, something like that. Okay. So we have the T1 is just operations with 0 and 1. So if you OR X with 0, you get X. If you OR X with 1, you get 1. The dual of that is if you AND X with 1, you get X. If you AND X with 0, you get 0. That should be pretty obvious. So as we go through these, if you have a question, go ahead and say something, and we'll talk about it. But does that confuse anybody or throw a wrench into your brain? Your brain works.
Identities, type of identity thing. The multiplication with the X and 1 and it's not like regular algebra. I'm sorry. Never mind.
Right. I mean, it sort of works like regular algebra, right? 1 times X will be X, 0 times X is 0. But what you're really doing is
I was just seeing some similarities.
Yeah, but don't let that seduce you, okay? Because you're actually not multiplying, you're ANDing. You're not adding, you're ORing. So here, if X is 1, 1 plus 1 would not equal 2. And if X is 1, 1 plus 0, well, I guess it would equal 1 then, but think of the 1 and 0 as true, false. Think of the plus as OR and the multiplication as AND. And we usually drop the little multiplication sign. We just write it out here.
So you're saying, so you're saying if X is 1 plus 0, then that's 0?
No, so whatever X is, X ORed with 0 is 0. Is X. Whatever X is here, X ANDed with 1 is X. But here, X ANDed with 0 is always 0. So if X is 1, it's 0. If X is 0, it's 0.
All right.
If X is 0 here, the result is still 1. What you should do is convince yourself these are true, right? Take a little OR gate, put in X equals 0 and in one input, put 0 in the other, see what you get. You get a 0. And now change X to 1 and see what you get. Now you get a 1. Right? Because if any input is a 1, the output is a 1 from a standard inclusive OR gate. All right, the idempotent laws. This is just where X ORed with itself is X, X ANDed with itself is X. So think about it. If X is 0, then obviously 0 and 0 is 0. If X is 0 here, 0 ORed with 0 is 0. 1 ORed with 1 is 1. So if X is 1 here, 1 ANDed with 1 is 1. Commutative. Doesn't matter how you write it. X or Y is the same as Y or X. X and Y is the same as Y and X. All the inputs to an AND gate, all the inputs to an OR gate are equal, and the order doesn't matter. Complements. So remember, when we write X prime, we mean the inverse of X. So if If x is 0, x prime is 1. If x is 1, x prime is 0. If you OR x with its complement, you always get 1 because one of them has to be 1. And all you need is 1, 1 going into the OR gate, and you get an output of 1. Here, when you AND x with its complement, it's always 0 because one of them's got to be 0. And if you have any inputs that are 0 in an AND gate, the output's a 0. Okay?
So it will never have a situation in that case complement for where you're gonna get a 1.
Okay, so let's say x has the value of 1. What's the value of x prime?
0,
So now you're ANDing 1 and 0. What should you get?
0.
That's right. Does that make sense?
Well, in a regular algebra, no, but I guess in this rule, yes.
Again, regular algebra has nothing to do with switching algebra. Nothing. They're just totally unrelated. What we're really saying here is true ANDed with false is true. I mean, is false. Sorry. True ANDed with false is false. True and ORed with false is true. All right, and here's the associative. If we have x, y, and z OR together, you can group them up. Now, what's interesting about this, same with the AND. What's interesting about this, and we'll see this when we talk about limited fan-in, even though in theory, our AND gates and OR gates can have an unlimited number of inputs, in the practical real world, that's not true. If you try and make an AND gate with gobs and gobs of inputs, you run into problems with responsiveness and impedance troubles and things like that. I mean, I guess you could do it, but normally what we do is we just add a layer, and we'll make, like, say we need a 9-input AND gate. What we'd actually do is we take 3 3-input AND gates and put those into one final 3-input AND gate, and that would give us an effective 9-input AND gate, but it would have divided it up into 2 layers, which does add a little extra propagation delay because now we're going through 2 gates instead of 1 gate. You could probably make a 9-input NAND gate. What if you needed 56 inputs? Then it becomes just ridiculous, and we never really do that. We would use gates with fewer inputs, and we'd create multiple layers. So, but if you try and do this trick with NAND gates or NOR gates, because there's the inverter on the output, it screws everything up and it requires an extra layer. And so it doesn't work. And we'll cover that later, but just keep that in mind. This works with ANDs and ORs. It doesn't work with NANDs and NORs. All right, and then the double inverse. If you take the inverse of X and then you invert it again, so X inverted and then inverted again, you get back to where you started. You get back to X. If you just take the inverse of X, then it's going to be opposite of X. But if you take the inverse of X and the inverse of that, you're back to X. There's no dual for this. It's,
Is it?
Go ahead.
I was gonna say, is this similar to what you do in discrete mathematics? Kind of the rules, some of the properties.
Yeah, I think that's true. But I'm not a discrete mathematician. I never took a discrete math course. I mean, I took a bunch of math, but I never took. I mean, and that's distinct from linear algebra. So linear algebra, on the other hand, is super important. Okay. Well, I suppose discrete math is important too, but I think it's, I don't know. Anyway, more at a theoretical level. All right, so that's the trivial theorems. These are all just straightforward. And you shouldn't have to memorize these. You should, after you think through them a couple times, you should just know them because they're obvious. All right. One thing that will come up a lot is when we OR X with 1, remember it's just 1. When we AND X with 1 or 0, we get either X or 0. When we OR it or AND it with itself, we get X back. And when we OR it or AND it with its complement, when we OR it, we get 1. When we AND it, we get 0. Those are good to know. Okay. The simplification theorem. So there are 4 of these. The S4, we'll cover it now, but I want you to kind of keep it, in the back of your mind. We're not going to really focus on S4. Okay, we're gonna leave it till we get to K-maps, because when you do K-maps, the consensus term becomes obvious. It's obvious why you don't have to have it, and everything kind of makes sense. And when you try and figure it out in just switching algebra, it really is confusing. So, but we'll cover it. You can use it if you want, but I will try to avoid giving you problems where you have to use it. You may have a problem where you could use it, but you don't have to. That could happen. But I'll try and avoid giving you any problems where you absolutely have to use it to simplify something or whatever. I'll try and avoid that. But when we get to K-maps, then we'll kind of embrace it a little bit. Okay, so here are the 4 theorems. You can combine terms. You can eliminate a literal. Remember, everybody remembers the definitions of terms, variables, literals. Somebody tell me the definition of a literal.
Wouldn't that be all the elements in the expression? Something like
No. So tell me what a variable is.
A variable is like a
Represents-
placeholder.
Well, it's like X, Y, Z, W, A, B,
Yeah.
C. Okay. So every appearance of a variable or its prime is a literal. So if you have a logic expression, every time a variable shows up, that's a literal. So for instance, here, in this top row, X is a literal, Y is a literal, X is a literal, Y prime is a literal, X is a literal. They're all, the variables are X and Y. Y primes per se is not a variable in itself, it's the variable Y inverted. Okay, so how many variables do we have in this expression here?
5.
No, you have 2,
Two.
X and Y, that's all there are. How many literals? You have 5 literals. So a literal is just every time the variable appears.
Okay.
And how many terms do you have on the left side?
2.
You have 2 terms. Are they and terms or terms?
There, it looks like an and or.
So you have 2 and terms. You do have 1 composite or term, but that's the whole expression. So when we say the expression on the left side, we know that that's an or, that whole expression is an or expression made up of 2 and terms, and then the expression is the 2 and terms ored together. So if I ask how many gates does that left-hand side represent, what's the answer to that?
Would it be 3?
That's right, 2 and gates and an or gate. Exactly right. So it's 3 gates, but it's only 2 terms. It's a little spastic the way they do that, but that's how they think about it. The whole thing's the expression, so that doesn't count as a term in itself really, but it's got 2 terms, 1 expression, 3 gates. And on this side, 4 literals, 2 variables. So this combined terms thing, this is so this side, we're looking at in SOP form. Over here, we're in POS form. And in SOP form, if you have XY ORed with XY prime, you can combine those 2 terms into 1 term, X, because the Y drops out because it changes. Here it's not prime, there it is. When you can actually combine these together, and that is just X. When you write the term X, so let's say you have a problem with 2 variables, X and Y, and it may sound funny, but if you write the variable X, you're immediately implying that includes XY ORed with XY prime. So when you just write X, you're actually including Y in it. You're including all the possible terms with Y, so you just drop the Y and Y prime. So you're including X, Y, and X, Y prime. So you just drop the Y and you just have X. If you do the same with Y, if you have 2 variables and you just have Y, well, let's say you just have Y prime. you're including x y prime plus x prime y prime. You're just automatically including that. And you can write those terms in if you want. Totally legal. You didn't change a thing because you can use this expression and turn them right back into, well, in that example, the y. In this example, obviously the x. So when we write xy plus xy prime, we can equally write that as just x. It means exactly the same thing. It's totally reversible. We can go both ways. If you have an x in an expression, you can substitute in xy plus xy prime, assuming there are two variables two variables that you're using, two variables.
Professor.
Yeah.
Does it really matter the order in which the terms appear?
No.
So it can be y prime x plus y x is still x.
Right. Yeah, remember the order, we grouped them here, doesn't matter. All the same.
Okay, just making sure.
Yeah, that's a good question, and that's good. All right. So here we do what's called eliminate a literal. And also look at the dual. So here we have it in POS form, x plus y quantity times x plus y prime quantity, just x. We can combine these two POS terms, or these two R terms, into just x and drop the y. We can also take x and expand it into this if we want. All right, now look at the eliminate literal. This is a little tricky, harder to see. X ORed with x prime y, this equals x plus y. This x prime goes away. Why is that? Let's do a little thought experiment. Instead of writing this out, because I don't have my overhead projector here, and it's hard to write. But otherwise, I'd write it out for you. But here, so let's say x equals 1. So when you evaluate this expression, if x equals 1, what you already know the answer to the expression. What is it? What does this expression reduce to if x equals 1?
1.
That's right. Because if x is 1 plus whatever, doesn't matter, even if it's x ORed with 0, it's still 1. What if x is 0? If x is 0, the first term x goes away, and now you're just dealing with the second term. And so x prime is a 1, so now the second term depends on y. So for the case where x is 1, this expression reduces to x effectively. For the case where x is 0, the expression reduces to y. So you can write the equivalent x or y. And you can drop this x prime. Now this is hard to see. This is probably one of the hardest things for students to look at an expression and realize they can drop that x prime. And over here, same thing. X times the quantity x prime plus y, you can drop the x prime and you just get x prime.
Professor.
Yeah.
Does y hold any values or only the x holds the values?
What? Both
Like
x and
those
y.
the 0 or the 1?
Yeah, they're both zeros or ones.
Okay, so is y able to hold any zeros or 1 or just the x term we'll be looking at?
No, y can hold a 0 or a 1. It's y is either true or false, x is either true or false. X
Okay.
prime is either false or true. Just the opposite of x.
And
Yeah,
same thing with the z, right?
Same thing with a z. Yeah, absolutely. So every variable is either 1 or 0, true or false. Well, think about this, but if you think, what you should do is write this down and then say, okay, let's suppose x is a 1 and y is 0. What do I get? Let's suppose x is 1 and y is 1. What do I get? Let's suppose x is 0 and y is 0. What do I get? Let's suppose x is 0 and y is 1. What do I get? And as you do it, you can do it for this expression, x plus x prime y, or you can do it for x or y, x plus y. And you'll see that for both sides, for all possible values of x and y, you will get exactly the same answer on both sides all the time, every time. So they are equivalent. And that's one of the amazing powers of switching algebra. There are only just a handful of possibilities here, because you only have 3 literals on the one side and 2 on the other. So you have a very small number of possibles for all possible values of X and Y. So you can write them all out in a truth table. And you can show that for all possible values of X and Y, both sides are always exactly the same. Therefore, it's proven. Same with all these things. All right, let's keep going through them. So eliminate a term. Here, this is one of the most powerful ones we have. So powerful, pretty powerful, very powerful. Okay, this is one that's super helpful. If we have XY ORed with X, we can completely drop the XY term. Now think about it. What if we had XY ORed with XY prime ORed with X? You could drop the XY and the XY prime, right? Because you already know XY plus XY prime is just X. And remember I said that you can substitute in for X these two values. So we could substitute XY plus XY prime right in here for this X, and we could write XY plus XY plus XY prime. Well, XY plus XY is just XY. So we could drop one of the XYs, and now we just have XY plus XY prime equals X. Well, you already know that's true because we did this one. So that proves that one. This is powerful because this term just goes away. And even if you had a term X, Y, Z, W, Q, L, T, F, P plus X, that first term would go away, assuming it has an X in it. Because all those other things are all assumed. If they're part of the problem, they're all assumed in X. All right, eliminate a term, or the consensus theorem. This is the one we're going to just look at, but we're not going to get wrapped around the axle about. And remember, this has a dual too. In its POS form, X ORed Y quantity times X equals X. All right. So eliminate a term. So here we have XY plus X prime Z plus YZ equals XY plus X prime Z. The way this happens, so here's look at the right side of this equation. If you have XY plus X prime Z, you can add a term YZ, and it does not change the value. Doesn't change the value at all. You will still always get exactly the same answers for all possible values of X, Y, and Z. And here you have that term added, the YZ term right there. That YZ term is called the consensus term. When we started implementing truth tables, sometimes we want the simplest solution we can get, and we don't want this extra YZ term, so we can get rid of it. But interestingly, sometimes because of timing considerations, our circuit has a hazard and we can get a false output. And so to fix that, we'll add this consensus term to fix it. So sometimes we do use consensus terms, even though they don't actually have, they're not actually required for the correct answer, but they might be required to fix a hazard because of timing considerations. And the timing considerations come into play when we have gates that have different delays than other gates, and when we have to have inverters on some of our variables. And the inverter throws in an additional delay that can cause a hazard. But we'll, like I said, we'll worry about that later. So I don't care that you spend a lot of time on this, but you should look at these three. Now let's cover these two conversion theorems. These are super important. And then we'll probably, maybe I'll work a couple of problems and then we'll quit here. I can't really do it with paper and pen very effectively. So we'll probably just, I'll probably save that for Wednesday. We'll work a whole bunch of them. And I'll work them out on paper for you. But I'm kind of limited today because I'm in my office. Okay. So we have the two C1 and C2. So these are the conversion laws, C1, C2, C3. C1 and C2 are on the same line because C2 is the dual of C1. So that's why it's a dual. And so these are actually two different laws, C1, C2. And this C1 is called the first distributive law, and C2 is called the second distributive law. This law down here has, I mean, it's kind of silly because I've written it out here. If you look at it, we've just flipped it around here, except that on this side, we've changed the X prime be with the Z, and here the X primes with the Y, but it does not matter. Either these are entirely equivalent. So the dual is not really different in this case, but I wrote it there. So there are three laws, C1, C2, C3. First distributive law, second distributive law, multiplying and factoring. And this C1 is pretty much like regular algebra, right? You can take X, multiply it in here, you get XY plus XZ. Now, of course, we're not really multiplying, we're ANDing. This is really orange, but you can kind of think of it that way. But this one, totally illegal in regular algebra. This is not legal. You can't do this. You won't work in regular algebra. Don't try it. But in switching algebra, it's totally legal and good. And it's a little confusing, but X plus YZ is equal to the quantity X plus Y times the quantity X plus Z. I put the little asterisk here because you can actually, if you have X plus WYZ, you can write X plus W quantity times X plus Y quantity times X plus Z quantity. And keep that in mind because sometimes you'll see X plus WYZ, and instead of having to use this law essentially 2 times or 3 times, you can just use kind of the alternate, just write it out directly because it's totally legal. So X plus YZ is equal to the quantity X plus Y times the quantity X plus Z. The quantity X plus Y times the quantity X plus Z is equal to X plus YZ. And then finally, the multiplying and factoring. So we have a X times Y and an X prime times Z. So we can take the X prime and add it to the Y and make that a quantity and multiply that times Z times X plus Z. Here we go. X plus Z quantity times X prime plus Y. And same thing here. We can go the opposite direction. If we have an X plus Y and an X prime plus Z, we can change that into X prime Y plus XZ. Okay. And then let me cover these last ones. Note that the first and second distributive laws, they're duals of each one. Okay. And then De Morgan's laws and duality. Okay, so here's how we do the inverse. We take all the, so we have an expression X, Y, Z, and we're going to invert it because we put parentheses around it, put the little tick out here. That just gives us, so we have to invert all the variables and all the operators. Well, what are the operators here? Well, we're ANDing X with Y and we're ANDing Y, that was Z. So we have, 2 operators, 2 AND operators there. And then we have 3 variables. So when we invert it using De Morgan's laws, we invert all the variables and we invert all the operators. So we have X prime ORed with Y prime ORed with Z prime. And here we just go the other way. Here we have X ORed with Y ORed with Z. We invert that and we get X prime, Y prime, Z prime, all ANDed together. The dual is exactly the same, except we don't flip the variables. So we do the dual of X, Y, Z, we just get X plus Y plus Z. And if you go back, all these over here are duals. These are all the duals of these. These are all the duals of these, except this bottom one doesn't really have one. Okay, that's it. That's all the theorems. So we have 6 simplification or trivial laws, 4 simplification laws, that's 10, and 3 conversion laws, that's 13, and these 2, 14, 15. So we've got 15 of these, although in all fairness, there's 2 here, so that's really 16, because the dual is a different law here. The other places, the dual is just the same thing in POS form, but here it's actually a different law. So 16 theorems or laws, and here they are. So here they are, and this is in the book. So you should refer to this frequently while you're working out these switching algebra problems. And you can certainly refer to it when you're working the problems on the test. So you don't really have to memorize them, but I will tell you, if you don't have them close to memorize, it means you haven't worked with them enough and you'll have trouble. So keep using them till you have them almost memorized. And these are so obvious, you really should probably not even have to memorize those. And so really, you only have to memorize, skipping the consensus term for now, 3, because the duals are the opposite. So 3 plus 4, 5, 6 plus really just De Morgan's law, 7. That's it. All right. And again, I'm not going to say write this theorem down from memory. I'm not going to do that. Okay, let me just show how we prove the second distributive law. So remember that the second distributive law is right here. X plus YZ equals the quantity X plus Y times the quantity X plus Z. Okay. So here's how we prove it. We have, what are our variables? Our variables are X, Y, and Z. So we list all possible combinations of X, Y, and Z. We have X, Y, and Z all 0. We have X, Y, Z 0, 0, 1. We have 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and all ones. And then we break out. So YZ itself we and Y with Z. So 0 ANDed with 0 is 0. 0 ANDed with 1 is 0. 1 ANDed with 0 is 0. 1 ANDed with 1 is 1. 0 ANDed with 0 is 0. 0 ANDed with 1 is 0. 1 ANDed with 0 is 0. And 1 ANDed with 1 is 1. So we only have 2 places where YZ equals 1. X prime YZ and XYZ. Okay. Now, if we add X to that, so we do X or YZ. So here's X. So 0 or 0 is 0. 0 or 0 is 0. 0 or 0 is 0. That's easy. 0 or 1 is 1. 1 or 0 is 1. 1 or 0 is 1. 1 or 0 is 1. And 1 or 1 is 1. Okay, so X plus YZ has the pattern for all possible values going down from 0, 0, 0 to 1, 1, 1 in order numerically. 0, 0, 0, 1, 1, 1, 1, 1. Now let's look at the other side of the equation. Okay, we've looked at the X plus YZ side here. Now let's look at the quantity X plus Y times the quantity X plus Z. Well, first we'll write out X plus Y, X or Y, then we'll write out X or Z, and then we'll write X or Y times or ANDed with X or Z. Well, so if we X or Y, well, X is 0, Y is 0, so that's got to be a 0. X or Y, 0, 0, it's a 0. 0, 1, it's a 1. 0, 1, it's a 1. And then all 4 ones here for X, we're going to have ones. So that this is 0, 0, 1, 1, 1, 1, 1, 1. And then we look at X or Z. So that's going to be 0, 1, 0, 1, 1, 1, 1, 1. Again, same kind of idea. And then now we're going to end these two columns together. 0 ANDed with 0 is 0. 0 ANDed with 1 is 0. 1 ANDed with 0 is 0. 1 ANDed with 1 is 1. 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 And 1 ANDed with 1 is 1. Now we compare the two green columns. This is the left side of the equation for the second distributive law, and this is the right side of that same second distributive law equation. Notice that for all possible values of X, Y, and Z, the green columns are identical. Okay, I'm going to stop with that. We'll work some problems and do some stuff. We'll finish up with this, and yeah, we'll finish and work some examples, and hopefully get you moving, because you'll find that this is well, there are some things to learn. Okay, stop share. Let me just take a minute and let you ask questions if anything popped into your mind. Go ahead. So did the theorems make sense to everybody, or are you like, is your head spinning?
Still kind of absorbing them. They made sense, but still absorbing the.
Yeah, it takes a little bit. I be perfectly honest. Switching algebras, it's tricky. I wouldn't say it's super difficult, but I would say students do struggle with it. And it's funny, in every class, there'll be there'll be one or two students that really like switching algebra. And they have a hard time with K-maps and the rest of the course, but they really like switching algebra. And then there'll be most of the students who don't get switching algebra, they love K-maps and they really don't have too much trouble with the rest of the course. So it's just one of those deals where it's just kind of funny. Seems like there's some people mathematically inclined and switching algebra really appeals to them, but then some of the other parts of the course they just don't like. And anyway, so don't be surprised if you're in the group that has trouble with switching algebra and finds it off-putting. But it's okay. I just want you to get a level of familiarity, a little bit of, get your feet wet basically, but you don't have to go for total immersion.
The theorems make sense, but I think I'll get a better understanding if there's like a couple examples of
Sure.
going through each theorem.
Yeah, and we will do that. We're going to use them. I'll try and do a lot of examples with them. So hopefully then they'll make more sense. And you'll see some of it's like, wow, that's crazy how powerful that is. And then other times it's like, I don't think I ever would have figured that out in a million years. I mean, there are some even like that for me, and I've been doing this for over 20 years. But okay, with that, then I think I'll bring off. You guys have a great Labor Day weekend. You should be able to do, I think you should be able to do the quizzes because I did set retakes up, even though the due dates may not have changed. So just go ahead and do the quizzes. If you have trouble, let me know. But I think everything should be squared away. And hopefully moving forward, we'll have a few less hiccups. I apologize, I just knew it was going to be like this. Some parts of it are out of my control. And I have to have the book people have to take my final draft stuff and make it into the online book. They have to do, it's all this HTML and sometimes they use a little latex and I don't know, it's crazy. So they're when they're actually building this, the actual underlying stuff looks crazy. So they do actually have to do some work. But anyway, I think they're getting caught up. It should be good. And then so we'll see. But one way or the other, we're going to teach you logic design this semester. You'll get it, and hopefully you'll find the book. If you have feedback on the book as you go through it, feel free to drop me a note. I'm sure there are a lot of corrections. There may be some things that need to be explained better. I don't know. I may have used polysyllabic words when I could have used simpler words. But I like to kind of introduce you to the lingo because this is the language you have to talk when you do digital design. That's what you have to know. You have to know all these terms. Assert, deassert. Active low. All those kind of things. Positive edge, falling edge. All that stuff those are really important concepts. And you have to have the right word. Just like when I did surgery. And you're telling your assistant what to do, and you tell him, I want you to grab the most distal portion on the anterior medial aspect. They have to know exactly what that means, and you have to use precise terms. And you can't just say, grab that thing there, or get a hold of that. Although sometimes we joke about that. And remember, one of the guys I operated with would say, he'd always use those words. He'd say, grab a hold of that. But he was being facetious because he knew that was kind of the common slang. He was just making fun of it. Anyway, probably a little arrogant, but he was a great guy, good surgeon. Anyway, so I want you to get a hold of these theorems. And I think you will. I want you to become familiar with them, and that'll be good. Okay, you guys have a great weekend. And let me just look at the chat real quick, make sure I didn't need it. Okay, good. Oh, but the quiz there 3 is asking me an impossible question. Okay, I'm not sure. You may have to Kyle, let me know what that impossible question was.
I was actually about to ask you on it. I'm not sure if I'm just not understanding what the question is asking for because like it says draw the equivalent circuit for the gate below and it's just a dialog box for me to type in. Is it asking for like the switching algebra?
No. That was the original quiz that I had done before they explained to me how these would actually be presented to students. So you're using the old quiz. That quiz should not be there anymore. It should be updated, and you'll have 10-question quiz. It's almost gradable. If it makes sense.
Okay, so will I have to request another retake so I can get the correct one?
No, you should be able to do it. You should be able
Because,
to
like-
log on. When did you actually do the quiz last?
Well, I tried doing it yesterday, but I just suspended it, so I technically still have like the time for it.
Well, so then so what you want to do is finish that and start it over. I think once you load the old quiz, it probably doesn't automatically replace it with the new one.
Okay.
So, but that's the old quiz, and that should be gone, should not be there anymore. But it may be living in a digital dimension until you refresh.
Okay, it says I can retake it. Thank you.
Yes, you should be able to retake it. All right, let's see. No class on Monday. That's right. Okay. Great. Everybody have a good time. Stay safe. Don't get drunk. Don't do drugs. Drive carefully. We'll see you later.